Hey everybody, welcome to the chemistry. Here's a little tutorial video. First video in classification of matter, that's the one with the ones next to it. In the processes, matter processes, that's the ones with the two next to it. Those are the ones we covered so far. And in this one, which is the third video, we're going to talk about Celsius and Kelvin. We're going to talk about specific heat. We're going to talk melting and freezing. And we'll get into a little bit of this stuff too on the bottom. So we're actually pretty much done as soon as this video is done with. So in terms of topics what we talk about. So here we go. Here's how it works out. So describing calculations in matter. All right. So first thing is, what are the formulas? Well, here are the formulas right here. How do you convert Celsius to Fahrenheit? Celsius is equal to Fahrenheit times 9/5 plus 32. Just plug in your degrees Fahrenheit and times 9 divided by 5 plus 32. There you go. All right, and then for the opposite, if you go from Fahrenheit to Celsius, it's going to be Fahrenheit is equal to Celsius minus 32 times 5/9. Very similar formulas. Notice they have the same numbers, but just one's just flipped. All right. We're going to use Celsius a lot in science. We're not always going to use Fahrenheit, but you will run into Fahrenheit and you have to convert some things. And then, but another temperature you guys are going to run into, another way of measuring temperature is Kelvin. Kelvin's is capital K, no degrees. Celsius plus 274.3. So then if I flip that around and I want to solve for Celsius, so degrees Celsius is equal to Kelvin minus 274.15. All right. So you have both ways to do it. All you gotta do is plug numbers in, add or subtract, make sure you know how to use your calculator. What is temperature measuring? Well, temperature is measuring, it's not measuring heat. Temperature is measuring average kinetic energy of the particles, how fast the particles are moving. Average being the key word. Okay? So when we're going from different phases, solid, liquid, liquid to gas, so on and so forth, they are going to be measuring how fast the particles are moving. All right, so temperature on a thermometer is basically your average particle speed. So like our temperature is normally 98.6. All right, that's how fast our particles are moving in our body. So when we're talking about particles that are moving and changing phases, we look at a graph. So here is a common phase diagram graph. Leg A represents a solid, leg B represents a liquid, and leg E represents the gas state. To go from a gas to a liquid, I'm going to condense. To go from a liquid to a solid, I'm going to freeze. But if I go the opposite way, solid to a liquid, I'm going to melt. If I go liquid to a gas, I'm going to boil or vaporize or evaporate. So what's happening here, if I'm going from a solid to a liquid and liquid to a gas, I'm adding energy. Notice I'm adding energy on the bottom here. This is heating calories, which is a form of energy. When I add energy, it's called endothermic. So we add energy. And then if I take energy away or I make the molecules slow down, because when I'm doing an endothermic process, I'm making the molecules move faster. When I want them to slow down, that's an exothermic. Okay? I'm taking energy. All right, taking energy. So think of a substance kind of like a child. If I want them to move faster, I give them energy. I give them sugar, so they're endothermically charged. Okay, like my kid, if you give him sugar, he's running around like crazy. But if I want him to calm down, I'm not going to give him any sugar. So that's going to be an exothermic. So taking energy away, and yes, sugar is a form of energy. If I wanted to skip this liquid phase and go straight from a solid to a gas, that's called sublimation, solid to a gas. Deposition is going from a gas to a solid. So know how those terms fit into this whole big graphical picture. So when I start boiling things and changing phases, I'm taking in and adding energy. And every substance takes a different amount of energy. So that's where we fall into specific heat. The specific heat is basically the amount of energy it takes to raise the temp by 1 degree. So some substances take more energy, some take less. Here is the formula for specific heat. Q is equal to M times delta T times C. Q is going to be usually in joules. It's going to be your energy. M is going to be the mass. Delta T is your temp change from start to finish. And then C is going to be your specific heat. All right, specific heat. So there's your formula for specific heat that we'll run into a little bit. So what would have a high specific heat? Water has a high specific heat. It takes a lot of energy to heat it up, and it takes a long time for it to cool down. So water would fall into that mix. All right. Takes a lot of energy to heat up, takes a lot of energy to cool down. What would have a low specific heat? Usually something like aluminum. Okay. It takes very little energy to heat it up, and takes a very short time for it to cool down. So specific heat has a lot to do with how long it can hold on to that energy and how quickly it gets rid of that energy. That's why we use metals for cooking, because they heat up really quick and they cool down fairly quick. All right. Whereas water heats up very slowly, but it also cools down very slowly. All right. So water, any type of metal is going to fall into the low specific heat, and water is probably going to be one of the higher ones. We'll talk about more later in the year. But there is your processes in describing change in matter. We got temperature up here, describing change of average kinetic energy. We see how things change through a graphical representation. Here's our formula we're going to be using in class for specific heat formula, and then we'll run through some examples more specifically in class, but here's your general notes. All right, so I hope this video helped. We'll talk to you soon.